The purpose of this video is to show you how to set up and run a model using GMS and Mt3DMS. So this enables the transport simulations in GMS. I made another video that gave somewhat of a brief overview, and so we're going to jump right in here. This is a an outline of what we're going to do. This file is available externally, so you can take a look at this and follow along. Step one is to set up the ModFlow model, and what I'm going to do is assume that we're using this model that was set up earlier in the class. This is the Clemson University campus right here, and we set up a model of the groundwater flow system in the vicinity of campus as an earlier exercise. That'll be the starting point for this exercise. So the first thing that we need to do is add Mt3DMS to the grid. So if I go here and right click, then I can see right here Mt3D, and we'll click on that. And this is the main setup page. So the first thing that we'll do is set up let's go here and set up packages. And we'll use advection, dispersion, and the chemical reaction package for this analysis. The output control, this allows you to save only a certain subset of the various time steps, so we'll set that at 5. And the stress periods. This allows you to set up the transient, kind of the basic overview of the transient part of the simulation, how long the model will run, and it will allow you to control the time steps that the model takes during execution. So these columns here are to set up the mod flow part. That will already have been done, and so we should have that checked off as steady state. The length of the time step will be 50 years. The units that we're using are seconds, so we'll use 1.5 e to the 9 seconds, which is approximately 50 years. And if we slide over here, this gives us some time step information about the Mt3D simulation. And so what we'll want to do is put in 1 e to the 6th seconds for the maximum time step. That's about 10 days or so, and that will fix and prevent the model from taking time steps that are too large. And we want to use this time step multiplier. This will increase the time step so that the model doesn't take too long to run. And for the rest of this, we'll just use the default, so we can hit OK there. All right, so we've got these basic first 3 buttons set up. Now we need to define the species. So this is the compound that we'll be tracing as part of the simulation, really is the main basis of this simulation. So we click New, and we have to give this species a name. So let's just call this TC. This is only going to be able to simulate a dissolve phase, and so we'll assume that we're simulating TC, trichloroethylene. The units, we'll just use the default here. This is the units that were used for the flow model. And let's see, porosity in the setup, I said, actually if you look at the next page in the PowerPoint, the porosity that I used here was 0.1. So we'll go and change all of them with this constant grid capability, and that sets all of the porosities to 1. So hit OK there. And that's going to be the setup that we need to do here. This is TC, and the starting concentration we'll assume is just equal to 0, which is the default, so we don't have to do anything there. All right, so let's hit OK. And that's the first step in the setup of the Mt3DMS. So that's still at step 2. Let's go down here to the next. Let's go over here and we'll go down to this. This is where we are right in here. This is a bit hard to see because of, well, let's see, we can probably blow it up. So we've gone through here, we set up Mt3DMS, the output control, the packages, we defined the species, and we did the stress periods, so we did this stuff here. And now we need to do the advection package. So that'll be the next step. And if we go up here to Mt3DMS in the menu and scroll down to the advection package, this is the advection package, and there are a variety of selections here, but the defaults will work for what we need right now. Okay, so we've got advection set up with the defaults. Now dispersion, we'll select this package, and the way this works is we put the longitudinal dispersivity in here. And for this problem, let's use a longitudinal dispersivity of 20 feet. So, or 20 meters actually. Meters is the basic length. So we'll select 20 and select OK, and we'll select OK here. And this is the transverse, horizontal, and vertical dispersivities. We'll just use those as the defaults, and this is the molecular diffusion coefficient, which we'll set to 0 for this problem. So we'll just use the defaults for those settings. And let's see, we need now the chemical reaction. This is where we'll specify the sorption, and we'll go right here. There are a variety of sorption models that we can use. We'll use just the linear isotherm. And what I'm going to do is set it up with a cell by cell configuration. Now, in order to use this linear isotherm, we have to specify the bulk density of the soil, and we'll do that by selecting this button here, and we'll say the bulk density is 1.6 grams per milliliter, and that'll be uniform. And then the sorption, the distribution coefficient here, don't worry about those units. We're going to use units that are consistent with the bulk density, and KD basically has to be now the inverse of the bulk density. And so for this problem, we'll assume a low value for sorption. We'll just use 0.01, and the units would be milliliters per gram, the inverse of the bulk density units. So we'll hit OK. This is a small value, and this will have really no appreciable effect for retardation. But if the sorption is greater, if we want to stimulate a different compound with a larger KD value, this is where we would enter that value. Okay, so that's all set up. That's going to be all of the packages that we need to set up here to define our problem. And so step 2 is now complete. So let's go here and we'll take a look now at step 3. Okay, step 3 is going to be going to a different part of GMS, the map data, model, and properties, and it'll set up coverages and allow us to put the contaminant sources here within the model domain. So I'm going to shrink this down a little bit. And the place we want to go here is to map data. We have this, I never really did rename this. This is just the default called new model. And you can see this is the coverages that I used to set up this model of the Clemson campus. So what I need to do is allow me to use coverages that will be used with MT3DMS. So if I go to the new model and properties, then I need to check off transport and select MT3DMS. Uh, that probably won't be set up already, but you'll need to do that. And then we need to go to define species and check this off, and this will be a default name of species 1. We need to make this the same name that we used when we set up MT3DMS up here in the grid. So we call it TCE. Okay, now once we do that, we can put in a coverage that will allow us to work with the contaminant. So we're going to assume that there are 3 sources of contamination in this model, and that in each one of the source areas, the concentration of the dissolved phase is constant. So to do that, we'll put in a coverage, and I'll rename it, let's see, source concentration. And I'm going to check off this box here, specified concentration, and we'll assume that the source is in the first layer. So we'll have this default layer range, and we'll hit OK. So there's the source concentration coverage. And now I'm going to go and put in the sources. Let's see, I'm going to zoom in a little bit. I'm going to assume that there are 3 sources in here. One of them is in Bracket Hall. Bracket Hall is where we meet for class. And so if we were to have a source of contaminants in Bracket Hall, okay, now I'm going to put in a source that's over by the motor pool, and we'll put another one in over on the other side of campus. Over here, this is the Brooks Center, the Performing Arts Center, so we'll put one in there. Okay, so we've put those polygons in. We build the polygons like so, and then we need to specify what the concentrations are in these polygons. So I make the polygons, I'm going to just do them all at once. So they're all specified concentrations, and I'm going to use 10 milligrams per liter as the concentration. Okay, so that's going to specify the concentrations of this source right here, right here, and right here. It's kind of hard to see these sources, but that's where they are. And if we go back here to the PowerPoint, we've gone through step 3. So we have our sources specified, and now what we need to do is map the coverages to MT3DMS. So we just did that, and we can also check the simulation and see how we've done as far as the setup goes, see if we can pick up some mistakes before we go and run this. Or there are no errors, but there is a warning that the concentration values for aerial recharge are all negative. That's okay for our problem. So looks good. We'll hit done, and then we'll go ahead and run the model. We'll save these changes, and now we're going to run this transient model. And so the model runs many time increments, and you can see each one of these several lines is a time step, and the progress of the model is shown here on the green bar. So it's going fairly quickly, but these models generally take a good bit longer than the flow models in ModFlow. We want to make sure to check this box right here where we read the solution on exit. If you don't do that, then you won't be able to see the results. Hit close. This is where the results are for the analysis that we just did. So if we click on TCE, these are the different time steps that we have. The the results are shown here for the TCE concentrations. Probably the way that it'll appear when you first see it is with contours. So it'll look something like that. These circles are put in by MT3D to indicate constant concentration. So let's turn those off. And now we see the concentration contours for what's the first time step right here. Okay, and we have 200 different time steps that are saved. So we can go out here and see what the plume looks like at a later time step. Now, the way we're viewing it is in the ortho mode. So this is a little bit confusing because we're seeing these different contours, the contours for different levels superimposed. So if we click on that, now we see it really just from one level. This is just from layer 1. And if we scroll up, we can see the concentrations at different layers. So this is the bottom layer, and you can see then we get a bit shallower, and that's what it looks like at the different levels. Okay, and we can also look at it then advancing in time. You can see that this getting a bit larger with time, and now at this many seconds you can see this plume has reached the stream and we're starting to have some discharge here, and it looks like it's splitting and it's headed over towards this surface water body as well. We go to the end of the simulation and we have a plume situation that looks like this. So there are the plumes, and I noticed here that the simulation ended at this many seconds. This is 10 to the 9th seconds. So this would be about 30 years. I wanted to go longer than that. So let's go and change the stress periods, or let's just take a look at the stress period setup. If we go to the basic transport package, go back here to stress periods. So there, that's the correct length, but I think what must have happened is one way that this model will stop is if it reaches the total duration of the analysis, which is shown here. But another way is if it reaches the maximum transport steps, 1,000. And that's probably what happened here. So I'm going to make this 2,000, and I'm going to hit OK. And I'm going to run this again. I need to map it to MT3D first, and then we'll try running this simulation again. All right, so now we've run the simulation a bit longer, and we've got the same configuration here, but if we go and select TCE and scroll down, we see now that it goes, there are 300 entries, and the last one is 1.5 times 10 to the 9th seconds. And so you can see that compared to the last one, we now have the plume advancing further, and it's discharging to this hole, both this stream reach and this stream right here. Up here, though, these plumes are a good bit shorter, and they don't reach the surface water, at least not in layer 1. We should check other layers, though. And you can see as we go deeper, these plumes get to be a good bit larger. And indeed, this is at the bottom of the cell, and it looks like this plume here that starts out from the motor pool, comes down, and it's discharging to this surface water right here. This is the Seneca River. So that's something that we see when we take a look at the lowest layer. And let's see, let's take a look again here at all three. So these are the three plumes, and what we can get from the simulation is that at this long time, the plumes are getting larger and more dilute as you go down deeper. So they're moving down vertically and then spreading horizontally, and the dispersion causes the concentrations to decrease. Nevertheless, though, these are the concentrations here. 0.01 milligrams per liter is still above the MCL for TCE. So if these really were TCE plumes, these would be contaminated water that we would have to deal with. We also see that the plume that starts here at the motor pool and this one at the Brook Center, those go in, in more or less a single direction, and discharge to the streams. This one here, though, at Brackett Hall, it's a little bit different. The Brackett Hall is up near the divide, and this plume spreads really in two different directions. So you can see that at Brackett Hall, there's a plume that's going this way and going to discharge to that stream, and another plume that goes this way, and soon it will discharge to this stream. So from a single location, we have the plume spreading in multiple different directions. And this is something that actually you might see out in practice. A lot of industrial facilities are built in uplands near groundwater divides, and they have plumes that emanate from them in going in different directions. Okay, so this is all pretty good. We can learn, I think, a lot about how these plumes might go. Now, one thing though that's going to be convenient is to get a little more of a 3D perspective on these plumes. So if we go back to ortho mode, and if we click on this symbol here, we can rotate this, and we can get kind of a 3D perspective. Now what we're seeing here is the contours in each one of the grid layers. So that's kind of cool. You can kind of see what's going on. Another way of displaying this is with ISO concentration surfaces. And so if we go to display and select the 3D grid data in display and go here, this is probably where you've gone before to adjust the contouring in GMS. And if we uncheck that and check ISO surfaces, this will, let's just take a quick look and see what that gives us. So here are some ISO surfaces, and basically what's happened here is that this mesh is following a constant concentration surface in 3D. And if we go back now to the setup, we'll go to options here for the ISO surfaces. We've got this ISO surface with this color. It has a lower value of 0.01, and then we go 0.01 to 2 and 2 to 10, and that gives us it's really just these two ISO surfaces that we have, and that gives us what we're seeing here. So we could potentially put in more ISO surfaces, but this shows, I think, pretty well this ISO surface here is the 0.01 contour, which is the MCL is 0.005, so this is a little bit above the MCL, but this is basically the leading edge of the plume. And then this zone in here is high concentrations within the plume. And so I kind of like this ISO surface perspective because it gives us a better 3D view of what these plumes are like. And you can see here on this plume, let's see, let me get the pointer. This plume here that starts off in Brackett Hall, how it goes down and then spreads out along the bottom of the aquifer. And really all of these plumes are, well, this one is doing the same thing. This one is spread, we can see here in the blue how it's going down, and then it'll come upward up and discharge to the streams. Okay, so that's all pretty neat. Gives us a nice view. We can change the time and go back in time and kind of select particular times and then step through this and see how the plume has changed with time. So that gives us also a nice way to visualize what's happening. And then there's one more thing that I want to show you that I think is really quite a nice feature, and that is the ability to render this as a video.